Hello. In this session, we are going to discuss a new chapter, electric field inside the met. So, we will be discussing some introductory concepts like atomic polarizability, polarization, difference between polar and non-polar dielectric, torque acting on a dipole kept at a uniform and non-uniform electric field. We know that matter, of course, comes in many varieties: solids, liquids, gases, metals, woods, glasses, and these substances do not all respond in the same way to electrostatic fields. Nevertheless, most everyday objects belong to conductors and insulators, or called as dielectrics. We have already talked about conductors. These are the substances that contain an unlimited supply of charges that are free to move about through the material. Now let us discuss about dielectrics. In dielectrics, all the charges are attached to a specific atoms or molecules, and they can move a bit within the atoms or molecules. Such microscopic movement of charges is not like as that of a wholesale rearrangement of charge in a conductor, but their cumulative effects account for the characteristics behavior of the dielectrics. Actually, there are two principal mechanisms by which electric field can distort the charge distribution of a dielectric atom or molecule, that is stretching and rotating. We will discuss it soon. Now just think what will happen to a neutral atom when it is placed in an electric field E? Absolutely nothing, because since the atom is not charged, the field has no effect, but that is incorrect. Although atom as a whole is electrically neutral, there is a positively charged core and a negatively charged electron cloud surrounding it. So when a field is applied, the nucleus is pushed in the direction of the field and the electrons in the opposite way. Or if the field is strong enough, it can pull the atoms completely, which is called ionization. With less extreme field, however, an equilibrium is soon established. For if the center of the electron cloud does not coincide with the nucleus, these positive and negative charges attract one another, and that holds the atom together. The two opposing forces, E pulling the electrons and nucleus apart, their mutual attraction drawing them back together, reach a balance, leaving the atom polarized. So when an atom is polarized, the positive charge is shifted slightly to one side and negative charge to other side, which creates a dipole moment. The direction of dipole moment is in such a way that is the same as in the direction of the electric field. This induced dipole moment is proportional to applied electric field, provided the electric field is not so strong. So we can write P is equal to alpha E, where P is the dipole moment and E is the applied electric field. The constant of proportionality is called atomic polarizability. The value of atomic polarizability depends upon the detailed structure of the atom in study. So, in a homogeneous isotropic dielectric medium, alpha is a constant, but in an anisotropic medium, polarizability changes to polarizability tensor, that it has a different values in different direction. So we can write matrix Px, Py, Pz is equal to alpha xx, alpha xy, alpha xz, alpha yx, alpha yy, alpha yz, alpha zx, alpha zy, alpha zz into Ex, Ey, Ez, and which is in the anisotropic medium. So different material responds in different way to the applied electric field. So the dielectrics are classified into polar and non-polar dielectrics. Now we will look what is non-polar dielectrics. This consists of a non-polar molecule Under normal condition, their centers of molecules coincide and each molecule will be having a zero dipole moment. When an electric field is applied, molecules orient themselves so that the substance as a whole will possess a dipole moment, which has the equation P is equal to Q into D. So, this induces an electric field E dash and is opposite to the applied field. Examples are air, hydrogen, benzene, etc. Now, we will discuss what is polar dielectric. For a polar dielectric, there exists a permanent dipole even though there is no electric field, but they are arranged randomly so that the net dipole moment is 0. But when an external field is applied to the dipoles, these dipoles reorient in the direction of the applied field, resulting in a net dipole moment. Here also, the induced field is in opposite to the applied field, and their examples are water, glass, ammonia, etc. Let us come back to the point polarization. So, we can define polarization as the relative displacement of positive and negative charges of an atom or a molecule in a dielectric medium under the influence of an external field. The external field means this field is external electric field. Or we can define polarization in another way. Since the application of field creates dipole within the volume of the dielectric medium, it can be defined as the induced dipole moment per unit volume. So, how will we write this? The polarization P is equal to P by volume, and here I will consider the volume as a small elementary volume d tau. So, the equation can be rewritten as P is equal to integral P d tau. Now, let us discuss a problem. Consider a primitive model of an atom consists of a point nucleus plus Q surrounded by a uniformly charged spherical cloud of radius a. Let us calculate the atomic polarizability of such an atom. So, as I told, in the presence of an external electric field E, the nucleus will be shifted slightly to the right and the electron cloud to the left, as shown in the figure. Because the actual displacement involved are extremely small, equilibrium occurs between when the nucleus is displaced a distance d from the center of the sphere. At that point, the external field pushing the nucleus to the right exactly balances the internal field pulling it to the left. That is, E is equal to E suffix E, where this E suffix E is the field produced by the electron cloud. Now, the field at a distance d from the center of the uniformly charged sphere E can be written as E is equal to 1 by 4 pi epsilon 0 q d by a cube. That is, the dipole moment P, we know that P is equal to Q into D, which can be rewritten as 4 pi epsilon 0 a cube into the electric field E. Therefore, from the equation, we will get the atomic polarizability as alpha is equal to 4 pi epsilon 0 a cube, which is equal to 3 epsilon 0 V, and as I told, V is the total volume of the atom. Next, consider another situation. A hydrogen atom with Bohr radius of half an angstrom, that is, and alpha is equal to 7.34 into 10 to the power minus 41 is situated between two metal plates 1 meter apart, which are connected to an opposite terminal of an 500 volt battery. What fraction of atomic radius does the separation d amount to this roughly? Since we know that dipole moment P is equal to Q into D, and which is again equal to alpha into E, and we have to find out what is the separation D. So, D can be written from these two equations. D is equal to alpha E by Q, and we know that from our old result E is equal to V by S, where S is the distance between the plates. This we have discussed in our old sessions. Substituting the value of alpha as 7.34 into 10 to the power minus 41, Q is equal to 1.6 into 10 to the power minus 19 coulomb, and V is equal to 500 volt, and as per the question S is equal to 1 millimeter, we get D is equal to 2.2 into 10 to the power minus 16 meter. So, the hydrogen atom will separate this much amount due to polarization. So, we know that if I apply a 500 volt potential between the hydrogen atom can separate to a distance of this small amount, that is 2.2 into 10 to the power minus 16 meter. We also discussed a point that if the field is more strong, it will ionize the atom. In this situation, let us calculate how much voltage or potential should be applied to the plate to ionize the hydrogen atom. So, just we have discussed the separation of the hydrogen atom. Now, we are going to discuss what amount of potential I should apply so that I can ionize the hydrogen atom. To ionize the hydrogen atom, the distance between the proton and the electron should be at least the radius of the hydrogen atom, and we can use the same equation as discussed before. Now, we have to apply a new potential. So, I wrote V as V nu, and I can write the equation as D is equal to alpha V nu by Qs. Here V nu represents the new potential and D is half of an Armstrong, because the distance between the proton and the electron is the half the radius of the Bohr atom. So, we will obtain V nu is equal to 1.09 into 10 to the power 8 volt. Now, just compare the strength of the field applied in both cases using E is equal to V by S and the new electric field due to the new potential E nu is equal to V nu by S, and convince yourself how an atom is getting ionized. Now, we are going to learn about a new situation in which molecules have a built-in dipole moment. In our former discussion, I took a neutral atom. So, what happens when such molecule, that is molecule with permanent dipole moment, they are called as the polar molecules, are placed in an electric field. Polar molecule is equivalent to an electric dipole with a positive and a negative center at a distance d between them. Assume that dipole is rotating about an axis through its center when a uniform electric field is applied, so that the positive charge experiences a force plus q and a negative charge experiences a force minus q, which constitutes the torque N. So, as per the diagram, the plus q charge experiences a force towards the right direction and minus q charge experiences a force around the left direction. So, the torque can be calculated as N is equal to R cross F. We know that the torque has the basic equation, torque N is equal to R cross F, and R is the perpendicular distance from the center of action. So, N is equal to R plus cross F plus R minus cross F, and this R plus has the value d by 2 from the positive charge and minus d by 2 for the R minus from the negative charge. So, N is equal to d by 2 cross force is equal to QE, that is from our former session we have discussed about force is equal to charge times the electric field and can be rewritten as d by 2 cross QE plus minus d by 2 cross minus QE. So, in total they have the equation QD cross E. So, the torque acting on a dipole kept in a uniform electric field can be expressed as N is equal to P cross E. We know that P is equal to Q into D. So, a polar molecule is free to rotate, will swing around until it points in the direction of the applied field. Now, we will check another problem. What will be the case when the field is a non-uniform field? So, when the field is more non-uniform, the things will be much tougher. So, if the force is non-uniform because the field is also non-uniform, so that the F plus is the force acting on the plus Q charge will not balance with the force acting on the negative charge, that is F plus and F minus will not balance each other. So, there will be net force on the dipole in addition to the torque. Of course, E must change rather abruptly for there to be a significant variation in the space of one molecule. So, this is not ordinarily a major consideration in discussing the behavior of dielectrics. So, the force on the dipole in a non-uniform electric field is, we can write F is equal to F plus plus F minus. So, which is equal to Q into E plus minus E minus, which is equal to Q into delta E. So, delta E is further represented as dE, which represents the change in electric field along the length of the dipole, since the dipole is very short. Therefore, we can write dE is equal to delta E dot dr. But dr is equal to d, that is the distance between the dipole. Therefore, more compactly I can write delta E is equal to del gradient of E dot d. Therefore, F becomes F is equal to P dot del E, where del E represents the gradient of the electric field. The total torque about the center of the dipole, even in a uniform electric field about any other point, can be calculated as N is equal to P cross E plus R cross F. This R cross F represents the, and P cross E represents the total torque. Now, we will discuss another special topic, which is the electric field due to a polarized object. Before discussing about an electric field due to an polarized object, first we will discuss about what is the potential due to an polarized object at a point P outside this polarized object. A polarized object has all the minute atomic dipoles aligned in a particular direction. The potential due to a single dipole at a distance r can be written as dV is equal to P dot r by 1 by 4 pi epsilon 0 r square. So, the figure represents a polarized object, and inside this object we will consider a small elementary volume d tau, and we will consider V is equal to V of r comma theta, that is the potential at a point distance r from this elementary volume. So, we will consider a small elementary volume, and due to that small elementary volume, what is the potential at the point P. So, we can write polarization vector P is equal to P by d tau, or the dipole moment small letter p is equal to P d tau, and from the first equation dV is equal to P dot r cap d tau by 4 pi epsilon 0 r square. So, the potential at the point P can be obtained by integrating the small potential dV due to this small volume. So, I have found due to this small volume what is the potential at the point P. Now, I am going to find out what is the total potential at the point P due to this small volume. So, V of r comma theta is equal to 1 by 4 pi epsilon 0 on integration on both sides we will get integrate P dot r cap by r square d tau. Now, the problem is how can we integrate such an equation, but from our mathematics we know that gradient of 1 by r is equal to r cap by r square. So, I will substitute this del of 1 by r to that equation number 2, which is V of r comma theta is equal to 1 by 4 pi epsilon 0 integral P dot del of 1 by r d tau. Again the equation is not solved. So, I have to use the relation del dot f a, where f is a scalar function and a is a vector. We have the relation f of divergence of A plus A dot gradient of F. So, here the scalar function is 1 by r and the vector is P. So, instead of F we can substitute 1 by r, and instead of A you can use the polarization vector P. And on rearrangement I will get the equation as V of r comma theta is equal to 1 by 4 pi epsilon 0 integral P by r dot dA minus 1 by 4 pi epsilon 0 integral 1 by r del dot P d2. The first term in the equation.